program to welcome you here tonight. My name is David Jamison. I'd like to welcome you to the second of our 2007 July Lectures in Physics, and I'd like to extend a special welcome to all our alumni in the audience tonight. The July Lectures in Physics have been running for a very long time, since 1968 in fact, and last week we found we had some people in the audience who were there at the first one, so we appreciate that interest in our program. The lecture series are aimed at addressing fundamental questions in physics, and our theme for this year is in physics breakthroughs. And last week we heard about the looming breakthroughs possible with the Large Hadron Collider, soon to come online. And tonight we're going to hear about quantum computing, more about that later. But next week I'll be giving a lecture on breakthroughs that actually weren't. And we'll wrap up the series the following Friday with a lecture by Andrew Malados on hidden mass and cosmic collisions. We now have the first images of dark matter in the universe. Now, before I introduce our speaker, could I just make a request for you to switch off your mobile phones, please? Lloyd likes very undisturbed line of thought. Undisturbed line of thought to convey some of these very difficult quantum ideas to you tonight. Well, tonight's speaker is in fact Professor Lloyd Hllenberg. He is in fact the newest professor in the University of Melbourne. He is now only 12 days old as a full professor, and this is an accomplishment of no mean achievement at the University of Melbourne. So I'd like you to join me in congratulating him. So this is his first public outing as a full professor at the University of Melbourne. Lloyd's major expertise is in theoretical quantum computing and theoretical quantum information. And he does the modelling of all aspects of the new type of machine we call a quantum computer. And he has a very illustrious international reputation in this field, and his papers have been highly influential. You are therefore getting a lecture tonight from one of the world's experts in the field. He does his work as part of the Australian Research Council Centre of Excellence for Quantum Computer Technology, and he comes with a Bachelor of Science and a PhD from the University of Melbourne, but he has spent considerable time overseas, including a stint in Europe as an Alexander von Humboldt Fellow, and in Japan as a Fellow from the Society for the Promotion of Science, and I believe he speaks pretty good Japanese even still. At present, he occupies the position of an Australian Research Council Professorial Fellow, and this is a position only achieved by Australia's elite researchers. He has a very impressive list of publications in the top physics journals, and he has been recognised for his excellence in teaching. Ladies and gentlemen, Professor Lloyd Hllenberg.
Thank you very much, everyone. After all that, I'll be embarrassed if I can't work my two pieces of technology. I'll blame the date. Thanks everyone for coming out on Friday the 13th. I don't remember drawing a short straw. I don't think I drew straws at all. So today I'd like to go through a little bit about quantum mechanics and the foundations of quantum mechanics, because I don't think we can really talk about quantum computers before we understand a little bit about why quantum mechanics is so wonderful and strange, and why actually we can't make any sense out of it whatsoever. Let me just put that up to start with, and this is actually what I like to read it as for a bit of solace whenever I'm scratching my head. So let's just go through very quickly how quantum mechanics came about, and I think a lot of you may have actually seen this story before, but it starts with Max Planck around at the turn of the century, early October in fact, and I believe it was a Sunday evening, and I like to think it was sometime around dinner time. That he solved one of the most important problems of the time, and indeed a problem that is still relevant today, as I'll talk about. And he solved what was called the ultraviolet catastrophe. And this is widely recognised as the moment that we began our journey on understanding the quantum view of the universe. And so what was the ultraviolet catastrophe? Well, one of the big problems at the time was you heat something up and you look at the colour of light coming off it. And it seems like a very mundane experiment to do, but just that one experiment has given us quantum mechanics and a view of the universe that we know today. So basically, as you heat something up, the colour changes, and you know we have expressions like red hot and everything like that. And the problem at the time was that if we looked at the amount of light coming off an object versus the colour of that object, data points would typically follow a curve like this, and there'd be a peak at a particular colour corresponding to the temperature of that object, and as we heat it up, the position of that peak would change. And then at the time, the best theoretical calculations would try to match it and would come up with a curve like this. It was okay sort of at the red end of the curve, but failed miserably down at the ultraviolet end, and this was called the ultraviolet catastrophe. And this was based all on classical physics at the time, and it indicated that there was something seriously missing in understanding. And then Planck essentially guessed this formula, and it matched it exactly. It's just amazing. It just follows all the experimental curves, no matter how you measure this, what substances you heat up, you will always get this sort of agreement. I have to say then, what is the connection with the universe as we know it now? Well, this is one of the things that we try to measure very precisely about the universe. Very early on, the universe was much hotter, and it subsequently has cooled down as the universe has expanded. And we can now measure the equivalent Planck curve of the universe through these wonderful experiments on the satellites and whatnot that do these measurements, and we find exact agreement with the Planck curve to such a degree that we can look at minor perturbations off that curve and deduce something about fluctuations of matter in the early universe. And so the Planck formula is incredibly precise. It's a very fundamental fact about the universe. So how did he come up with it? Well, it turns out that his reasoning eventually to justify his guess had to assume quite an amazing hypothesis at the time, which was that energies inside atoms had to be quantized. And that's why we believe this is like the birth of quantum theory. So the hypothesis to explain the origin of that curve itself, to go through a statistical physics analysis of why that curve could come out, had to postulate that the energies of atoms, when you heat them up, come in discrete quantum amounts. So that the energy of atoms was actually quantized. This is the birth of quantum theory. Okay, so just going through a very quick timeline of quantum theory. Well, first of all, there was Planck's hypothesis that energies were quantized. And then along came Einstein. There were many other people involved, of course. I'm just going through a very quick sort of rundown of who did what. And he said, well, maybe it's not just atoms that are quantized, the energies of atoms that are quantized. It could also be light itself. And so he came up with the idea of a photon, a particle of light. And then he showed that, well, diffraction experiments showed that light could not only just behave as a particle, but also as a wave. And so we had this sort of wave-particle duality of light. And it turned out, well, this is one way that I'm going to draw such an object throughout this lecture, which is a blob, which can behave as a particle, but in some sense also has a wave-like nature. So if you just forgive me, that's my artist's impression of a photon for this lecture. But it turns out, and this is following de Broglie's work, that everything has this amazing duality. Everything has this wave-particle nature about it. Electrons, even atoms themselves do, and even large molecules can have a wave-like nature as well as particle-like nature. And so quantum theory is basically saying everything is behaving as both a wave and a particle. And in some of the very basic equations that we know in physics, here's an equation relating the energy to the frequency for a photon, and the momentum and the wavelength of a photon. Don't worry about how this comes about. But the interesting thing is that on the left-hand side of this equation, or both of these equations, we have particle-like features or properties, energy and momentum. And on the other side, we have frequency and wavelength, which are wave-like properties. And these are connected by a thing called H, which is Planck's constant, which is the constant he needed in his formula to make everything work out. Okay, so if we have a look at the modern version of quantum theory, well, we still use Schrodinger's equation a lot. That describes non-relativistic quantum mechanics. When we combine relativity and quantum mechanics, we get what's known as quantum field theory. And that's been one of our most successful field theories. If we try to calculate something called the electromagnetic moment, which is the way, basically describing the way an electron behaves in a magnetic field, in quantum field theory we have to calculate a whole bunch of Feynman diagrams out to infinity, but the contributions get smaller and smaller and smaller the more complicated those Feynman diagrams get. These are basically, a solid line is the electron itself, and a wavy line is either a real photon or a virtual photon. But the point is that if you calculate just based on the theory, quantum field theory, all these diagrams, you get a quantity from the theoretical side, which is on the top there, and the most amazingly, exquisitely precise measurements of this quantity now agrees very, very well with theory. So this is one of the hallmarks of quantum theory, indeed quantum field theory, that we get such agreement with experiment. From then, we got, and this is obviously skipping a lot, we've got the standard model of particle physics, and we heard Jeff Taylor talk about that a lot last time. And from there, people are looking at trying to unify all the forces, including gravity. And so we've got all these new theories, superstrings, supermembranes, and handbags. I'm not being totally silly there. That's all about topology and handles in space-time and so forth. And then the latest on this quest to understand quantum theory and develop it is the idea of quantum information. That's really what I want to get to the heart of today. And out of that, we're seeing some very interesting technologies, applications, things like quantum communication and quantum computing, as well as a bunch of others that people are just trying to dream up now. But these are the two that I really would like to talk about and explain enough about the weirdness of quantum mechanics that allows us to start thinking about this sort of technology. Okay, so how do we try to understand why quantum mechanics is so strange? I mean, that sounds like a weird thing to try to do, but the canonical way that we get into understanding why quantum mechanics is so startling is to think about this effect of two-slit interference that we know and love from water wave experiments. Okay, so if you had a simple ripple tank there and you had two sources just dipping into the water like this, you would produce two sort of spherical wave fronts that would interfere, and out here on the screen somewhere you would see a pattern, an interference pattern of light and dark fringes, corresponding to constructive and destructive interference. Well, it turns out you can do the same thing with light. If you have a laser and you shine a laser at two slits that are at an appropriate distance apart and size for the wavelength of that light, like so, then the two slits will act like little sources, little point sources as well, and you'll get interference of those light waves, just as water waves do. And when they appear on the screen, you will see an interference pattern which is essentially the same as that which you get from the water wave case. It turns out that, well, we understand a laser wave as consisting of many, many, many photons all at once, and so they behave on average like a wave, and not surprisingly, it has the same mathematics as for a water wave. But the really interesting thing is when you say, okay, imagine I turn my laser right down to the point where only one photon comes out of that laser at any one time. Okay, that's when it gets really interesting. So we imagine I've got my blob here, which is my photon, which can sometimes behave as a wave, and it's incident on this two-slit apparatus. Okay, so what's going to happen? Well, I was hoping to get, we do have a single photon source down in the basement, and I was hoping to get an optical fibre here to actually show you this experiment, but we couldn't do that. So I've got some theoretical simulations here. If you just let 100 photons go through and then you have a look at what's happening on the screen, you can just sort of see a few points of light. As you let more photons through, you see there are more hits on the screen, and you start to see a band forming. And then you see a central band forming and and faint bands either side, you start to see an interference pattern. The interference pattern builds up as you have more photons going through that two-slit apparatus. And finally, if you have many photons, you really see the pattern clearly. Okay, so you think, oh, well, okay, I'm getting the same interference pattern as I get when I shine a laser wave through it. What was the point of doing one photon at a time? Well, the point is, from the point of view of describing this as an interference effect from waves, how do you get that one from one photon? If the photon is behaving like a particle, what is it interfering with to produce an interference pattern if there's only one going through that apparatus at any one time? So that had people really scratching their heads. And well, if you cover up one of the slits, the pattern disappears. And so obviously the photon knows about the two slits, but it's only one photon at a time. So how can that be? Well, we'll just say that it's both. It's both a wave and a particle at the same time. So that's the origin of wave-particle duality, and it's actually built into the mathematics. If you look at the mathematics of quantum field theory, you can actually see when you write down the expression essentially for a photon, what it actually is, you see parts of the mathematics is telling you, oh, it's a wave, and other parts of it are telling you that it's actually a particle. It's actually enshrined in the mathematics now. Okay, so the obvious question is, well, how do the photons know to build up that pattern? Okay, how do they know that they're going to be part of, when they hit the screen, part of an interference pattern? Well, quantum mechanics, once we learn how to solve the system using Schrodinger's equation, actually tells us what the pattern should be for a single photon. That's called the wave function. And that's denoted by this thing, Greek letter capital psi. And where that turns out to be large, there's a large probability, or high probability of seeing that photon at that point on the screen, but you don't know exactly where it's going to be. The photons hit the screen at random. Where that's small, there's a low probability. And so if we describe it in quantum mechanics, we would actually derive mathematically this quantity, the wave function, and where that turns out to be small, and it's a function of the distance along the screen, where it turns out to be small, we don't expect many photons to actually hit. And this is central to quantum mechanics in the interpretation of the Schrodinger equation. We don't know exactly where any photon will hit the screen. We can never know that. That's just completely random, or almost completely random. Because what we do know is the wave function, if we were to calculate it. And the wave function tells us the probability of where it might hit the screen. And that's all we can ever know about things like photons and electrons, the probability of where they might be at any given moment in time. We can never know exactly where they were until we do a measurement, and then we might know a little bit about these objects. Where the wave function is large, we expect to see a photon hit the screen with higher probability. And so it's this wave function which is determining this interference pattern. So we never know where an object will be, we can only ever know where it might be. And that's essentially the way reality works. Okay, so let's have a look at what this means for our photon and how we actually try to interpret what happened. We've now talked what happened out here. We've talked about the photon really being this sort of wave particle object there. But what is it before it hits the screen? Okay, so it's one photon, and we consider it as having gone through both slits. Okay, so it's one photon, and it's essentially a combination of two possibilities at the same time. And so one possibility is that it went through slit A, and another possibility that went through slit B. The way we describe it is exactly like that it's two possibilities, and we don't know which one it is until we put a screen there, and it hits the screen at some point. And that's telling us something about that photon. So it's still one photon, but it's two possibilities. And until it hits the screen, we actually don't know anything about where that photon actually is in between. It's in this indeterminism zone where there's no objective reality. Okay, we can't say. That means we can't say that it's gone through slit A sometimes and it's gone through slit B other times. It's actually gone through both. That's the thing that's really strange. So we describe that mathematically in a very simple way. We say that the overall wave function is just the sum of two possibilities, a wave function corresponding to it going through slit A and a wave function corresponding to it going through slit B. You can imagine those two wave functions are like the two sources of light that are produced by the two slits. And those two things essentially interfere with one another to give an interference pattern described by the total. But I should stress, we still don't know whether it's gone through slit A or slit B there. It's actually gone through both. And the two possibilities create the interference pattern. There's no point trying to understand this. Nobody understands it. Right? But this is the way it seems to work. This interpretation that I'm just giving you seems to be borne out by all experiments, and it actually gets worse, let me tell you. Okay, so we describe the system like this as indeterminate. But it's interesting to think, okay, well, what if I didn't block off one of these slits, but I actually tried to take a very sneaky peek in this region here, and try to figure out, without disturbing the photon, can I see whether or not it went through slit A or slit B? As soon as you try to do that, you destroy the interference pattern. Okay, you've actually determined the reality, the objective reality in the centre there. You've determined that if you actually see it here, it's gone through slit A. And if you saw it, and if you didn't, it means it's gone through slit B. And so you've determined that it's gone through one or the other, and it can't produce an interference pattern. Okay, so the act of looking at it destroys the interference pattern, destroys that indeterminism that we had in the middle. And we call that wave function collapse, that the wave function went from this sum of two realities through a process of sneaky peeking to one or the other. Okay, we collapse the wave function. And this happens also, people have done these experiments on two-slit interference for electrons and atoms. And I think the record is a 60-atom buckyball gone through a two-slit apparatus. And you see interference patterns. So, and the reason you can't do it for humans, there are many reasons you can't do it. Ethics clearance wouldn't allow you to do that. And also you wouldn't be able to get the slit width down far enough and squeeze something. Never mind. Okay, so it gets worse. And Einstein was very concerned about this sort of interpretation. And he got together with Podolsky and Rosen. And they came up with an absurdity, what they thought was an absurdity of quantum mechanics. And they said, okay, well, let's say that that's true. And let's take two photons now, and I'll make one. This wasn't exactly their argument. I think they were using electrons, but let's take two photons, one blue and one orange, just to continue the theme of photons. In the same way that I could produce this superposition of two possibilities of going through slit A and slit B, I can in the lab, well, I can't personally because I'm a theorist, but I know other people can. You can, in principle, produce a superposition of a blue photon and an orange photon. So these can exist simultaneously, describing the one photon state. So it's a single photon with two possibilities. Okay? It gets worse because now if we have two such objects, okay, we can make not this state with one photon, but we can make with two photons now. We can make a state which is a really weird combination called an entangled state. And it's made up of two possibilities. Okay, one possibility where photon 1 is blue and photon 2 is orange, but together with another possibility where photon 1 is orange and photon 2 is blue. And this is together in the same way that through the two-slit experiment the two possibilities coexisted at the same time. So you can make this particular entangled state. But these two possibilities exist simultaneously before you actually observe which colour any of the photons are. Okay, so let's have a look at what happens if we observe such a quantum state, this entangled state. Well, we will either get this possibility, where photon 1 is blue and the other one's orange, so it collapses into this possibility, or we get the other one. And which one we get is completely random. The way I've written it there, if that was mathematics, then I'd have a 1 on root 2 there, and it would be a 50% chance of getting this one, and a 50% chance of getting that one, but completely at random, like tossing a coin. Okay, so that means if I measured photon 1 as blue, I don't have to measure the other one, because I know that it's going to be orange. And if I measured photon 1 as orange, I don't have to measure the other one, I know it's blue. Okay, and this is central to the argument from Einstein, Podolsky, and Rosen. They said, how does photon 2 know which state to be in? How did that happen? That if I measured photon 1, how does photon 2 know that? And we're going to take this to the extreme in a moment. And so they said, the only way photon 2 can know what you get as a measurement of photon 1, because I can separate them, is some form of instant communication. In other words, communication faster than the speed of light. And of course, Einstein said you can't do that because of my special relativity, and that's not a quote. But he said, well, that's obviously not allowed, and so therefore your theory of quantum mechanics is incomplete. It describes this absurd situation which needs instantaneous communication to resolve it, hence it must be wrong. And so that's what I mean. They came up with this absurdity, threw it out to the community to say, right, what do you think of that? Your quantum mechanics is incomplete. It turns out that you can make these states, and people started to do this in the 80s, and I'll give you a timeline in a moment. But let's just take this to the extreme. So I'm going to describe this as, before I measure it, I've got photon 1 over here and photon 2 there, but I don't know what colour they are, because I don't know if I'm in this possibility or this possibility. I'm in both at the same time. Okay, so I draw them as sort of a PowerPointy sort of combination of both colours. And I note that they're actually existing in two possibilities at the same time, one where this is orange and that one's blue and vice versa. And now I separate them over an extreme distance, a distance over which light takes a very, very long time to travel. And I'm pretty confident that if there's communication between these two photons, it would have to be pretty much instantaneous. And so at the ends of the galaxy, and I don't know which galaxy this is, I have my photon here, and one's being measured by Alice, and the other one's being measured by Bob. Okay, so let's say now Alice makes a measurement, and Alice measures the photon as orange. So she makes a measurement on her photon. It's indeterminate before she makes the measurement. It's in both realities at the same time. She measures orange. So what if Bob, almost at the same time, just a microsecond later, certainly at a time very short compared to any sort of signal that could get across the galaxy, measures his photon? He has to get blue. And if you do these experiments, that's exactly what happens. So there's my clever PowerPointing. Took me ages to do that. I don't know if you want to see that again, but I'm very proud of it. So Alice measures her photon as orange. The entangled state has collapsed into the reality where it's orange and blue. Bob has no choice but to get blue when he measures his photon. Oops, sorry, I didn't mean to do that. Okay, so the wave function has collapsed into the particular reality where, whoops, that should be the other way around. Serves me right. That should be orange, that should be blue. Okay. That's just in there to see if you understand, of course. So there are two possibilities. Is Bob's state determined instantaneously? And this is kind of what quantum theory is suggesting. Or was it predetermined? Were these photons actually in one or the other reality, but we just didn't know it? And that was the preference for everybody, because there were two evils here. One evil was non-locality of physics. That meant that something that happened here instantaneously influenced something on the other side of the galaxy or universe. Right? Something instantaneous, and physicists don't like that. And even now we're very uncomfortable with it. The other evil is basically that, well, there was something about the state that we didn't know, and so we call this hidden variables theory. Okay, so was it all predetermined but we didn't know it? Or do we have instantaneous interaction? In other words, is there basically reality that it's either one or the other, objective reality, or is there instantaneous communication, it's one or the other? Okay. Oops. Okay, so these are the options, to summarise. So quantum theory would say, if we make such a state, then it's existing in both realities at the same time. And when we make an observation, we get either this particular reality or the other one completely at random. Okay, so the other option is the one that was probably favoured by most people, good old human intuition, local realism. That is that it was actually this one or the other one before observation, it's just that we didn't know it. And there's something incomplete about quantum theory. There are these hidden variables which means that if we knew enough about the system, we would have actually been clever enough to know which one it was. Okay, because it can't possibly be both at the same time. That just doesn't make sense. That means that there's no reality until you make a measurement. Okay, so how have events actually panned out over the years? Well, 1935 was when Einstein, Podolsky and Rosen posed this paradox. So it was a challenge to the validity of quantum mechanics, and it was basically saying, well, quantum mechanics must be wrong because it implies instantaneous influence. John Bell in 1967 came up with a beautiful way using photons to actually test out these ideas, an experiment which, when you look at the results, you could say quantum mechanics is wrong, hidden variables theory or local realism is actually right. And so then experiments actually caught up with that, and in 1982, Alain Aspect did the experiment and found in favour of quantum mechanics, that these spooky correlations between Alice and Bob actually do exist. And so local realism failed that test. So people started to get a little bit nervous, and it was a matter of, well, which one to ditch? Do we ditch reality, the fact that these photons were in no objective reality until we measured it, that observation created that reality, or do we ditch locality and we allow instantaneous interaction across great distances? These are the two evils, two things that you have to choose between. And then just recently, Tony Leggett, who did a lot of fundamental work on how environments will interfere with quantum coherence, and a little bit about that later, came up with an experiment to nail which one of these you have to give up. And he said, well, before we look at that, he basically found a way of including instantaneous interactions in a meaningful experiment, so that you could at least put that in and see if you then can keep realism in your theory. Okay, so this year, in April, was published a paper by Hllenberg's group in Vienna, and basically they tested this result of Leggett, and they found in favour of quantum mechanics. So local realism fails in his paper in Nature. So basically, this is the end of realism. There's no objective reality. So even allowing for instantaneous interactions, measurements still didn't agree with that theory. You have to describe things with quantum mechanics, and in quantum mechanics there's no objective reality until you do a measurement. Okay, so if this is making you uncomfortable, just sit there for a second. I was going to get a little video of Teletubbies for a few seconds so you can just get over that shock. Okay, so that takes solace. There is an alternative to this whole idea of wave function collapse and everything, which makes everybody uncomfortable. And so this is the so-called many worlds hypothesis from Everett. So if we look at our system, our quantum mechanical system, which we now describe as being in two realities at the same time, not in any one of those realities, and we can make, Alice makes a measurement and collapses a wave function into this possibility. I've got it the right way around now, orange and blue. Or there's another possibility where Alice measures blue. Okay, instead of the wave function having to collapse, which is very ugly in the theory, we'll postulate something else, and that is that the universe splits into two possibilities, where each of these scenarios is played out in a very smooth way, and you don't have to worry about wave function collapse anymore. So I don't know if that's better or not. But anyway, so people grapple with this whole idea of wave function collapse. Still now, it's a very active area. People don't understand, we understand quantum mechanics up until this point of wave function collapse, and trying to understand the act of measurement is a very important area of research in quantum mechanics right Okay, another cute thing that people noticed, and this, I suspect, since 1935, I suspect quite a few people noticed this phenomenon of quantum teleportation, but they're probably a little too embarrassed to say anything about it because it's a rather easy extension to the EPR paradox. But it took a long time for this to come to consciousness, in fact only in the last 10 years of modern physics. And that is if we introduce a third particle and we entangle that with Alice, and Alice's particle is entangled with a particle that Bob has. There's a certain sequence that we can carry out measuring these two particles here, and you'll notice that this one is subtly different to Alice and Bob, right? It's got a little bit more blue because it's in a slightly different superposition. There's a way to do the measurements over here such that when you do that, this particle here is now imprinted on Bob's photon over there. You haven't physically transported the particle instantaneously. You can't do that. That does violate special relativity. But because these are all identical photons, a photon is a photon after all, what you can send instantaneously is the state of the photon that was here and imprinted on the state of the photon that's over in Bob's lab over there. And that can pretty much happen instantaneously. And it has been shown in the lab, and it's actually done routinely now in various labs around the world. Okay, so an obvious question is, could you then use entanglement and all these connections between particles to send information instantaneously? The answer is no. And that's related to a so-called no-cloning theorem of quantum mechanics. But you can send this influence. It's a kind of very subtle distinction. Okay, well, it probably, at the time when quantum teleportation came out, lots of people thought Star Trek and, well, could you ever use that to actually teleport a physical substance or object over distances like that? And so this is what we all know as teleportation. This obviously has time dilation in it as well, so I can apply the temporal corrector. Okay, but this is pretty much impossible because the vast number of particles involved, or so people thought. Just recently, we've completed some work which shows that you can get something like this in spirit on a cloud of atoms. There's a way now of cooling atoms down to very, very cold temperatures, like microkelvins. And when that happens, they all behave as if they're in the same quantum state. And it's called Bose-Einstein condensation. There are all these beautiful quantum mechanical effects that people are now measuring. And so what we've shown theoretically, but we believe people could do the experiment, is, well, here's my cloud of atoms there, and we're just looking at the surface of this cloud. And we're in a potential well that's got 3 minima. Okay, so this is a potential barrier that a classical particle wouldn't be able to get through. It'd be like trying to get through a brick wall. But we know quantum particles can actually tunnel through such barriers. And we're so familiar with that now, we don't think that's really strange. But what we'd like to do is, and none of my co-authors, this is done by Andy Martin's group and my group here in the school, none of the authors are really comfortable with the word teleportation yet, but I like bandying it around, so I will. What we'd like to do is teleport this cloud of atoms over to that region there without going through the middle region. That's what we'd like to do. That's sort of the principle of teleportation in the Star Trek sense. Okay, so here we have a little movie. We found a way to do that. And here we see the cloud shrinking a little bit as we adjust the potential barriers, and it disappears from here, appears in the third barrier without ever going through the intervening region. Okay, so what we've done is we've raised and lowered these barriers, but we do it in a really counterintuitive way. We actually lower the furthest barrier first and then the closest one. And in doing that, it actually hops all the way over. If we lowered this barrier first, it would hop into the centre well. And then if we lowered the next one, it would hop into the third one. But that would be teleportation, right? Because that would just be hopping around. But there's a way to do it in this counterintuitive sequence where you lower the furthest barrier first, then lower the nearest one, and it goes from here over to there like the movie shows. Show you that again. So it basically disappears. We turn the teleporter on. I never thought I'd say that in a lecture. And it appears up there. So we're just gearing to submit that for publication. It would be interesting to see what people make of it. Okay, so that's the preamble about quantum mechanics. And I'm very interested in the foundations of quantum mechanics, but I'm very cognizant of the fact that you could get driven nuts by trying to understand it. So for me personally, this was a good motivation to get into the whole area of quantum technology. And that's sort of like mundane applications of quantum mechanics, which when you're trying to achieve the outcome of that application might help you to understand the underlying theory a bit more. And so around what we now define as quantum information, and I'll define that a little bit later on, we have this interesting connection that we get. First of all, and this is not chronologic the way this was done, but we do know now that if you had a quantum computer, one of the things it could do is crack cryptographic codes. Okay, that's one of the problems it can do. But it turns out that quantum mechanics also allows you to define a channel of communication, as it turns out using single photons, which is absolutely secure, that you can't crack. And so here we have quantum technology which could crack cryptographic codes, and here we have a way of using quantum mechanics, quantum cryptography, to send data absolutely securely. So it's kind of this weird connection of quantum mechanics and quantum technology through the whole cryptography area, which is to say classical information theory. Okay, so how might you do this? Well, it turns out that we have a very active program in both areas. One of the things I work in is this whole idea of quantum cryptography, and that is using a protocol called quantum key distribution to send data through an optical fibre channel using single photons. So the first thing you have to have is a bona fide, very reliable single photon source. And that's what we're doing here at QCB, Quantum Communications Victoria. It's been funded by the state government. And it's based on the following idea that was come up by Bennett and Prasad in 1984. And that's the idea that Alice wants to send information to Bob, and they have a classical channel that they can send encrypted data. But that data is protected by a key, and they want to send the key over a secure quantum channel. And they can do that by sending single photons across that channel where the polarization of the photons, which is to say the direction of the electric and magnetic fields, encoding ones and zeros. We can organise a polarizer to polarize photons diagonally or vertically and horizontally, and we can just say, in one case, a horizontal is a 0 and a vertical is a 1 and so forth. We can encode information on the photons and send them down through the channel to Bob. And the thing is, if we have an eavesdropper, Eve, so these are the members of our team, and here is our CEO here, Shane Huntington. His job is to, well, A, worry about gender issues there, obviously, but to try to intercept the photons and try to get some information extracted from that channel. And the idea is that if he tries to do that, yes, he can grab a photon, but if he tries to measure its polarization, he just gets random numbers. And he can only make sense of them if he knows how Alice prepared that photon. Okay, and the thing is that Alice and Bob can detect whether or not somebody is listening, because when you take a photon and you measure it, then you've got to replace it into the stream in the communication channel. Otherwise, they know that there are fewer photons than they expect, and they know somebody's listening. If Eve tries to resend every photon that is captured, the way that the protocol works is that Alice and Bob will see that resend attack as increased noise. Okay, so this is a very robust way, an absolutely secure way of sending information, but to do it you need a source, a true source of single photons, and that's been quite a technological challenge that people are trying to work out all around the world. So here is the way that we're trying to do it. Just briefly, we have an optical fibre, and on the end of the fibre we have a little chunk of diamond, a nanocrystal of diamond. And diamond is an amazing material. One of the things it does is when you have some defect, a particular defect in its atomic structure involving a nitrogen and a vacancy, no carbon next to it, then it has beautiful properties in that if you shine a laser on the diamond and it hits this part of the structure, it excites it into an excited level, and it drops down and will spit out reliably a photon of a particular wavelength. So it's got all the properties that you want for a single photon. Well, they don't look perfectly sort of cut and everything like this when we put it on the fibre and we grow them, and they look like these sort of blobs. That's the core of the fibre there, that round thing, and these blobs are synthetic diamond that has been grown. And then you can figure out which one is the single photon emitter and so forth. So a key thing is to know how good is your single photon source. And there's a particular experiment you can do. You put the photons through a beam splitter, and then you detect after a certain amount of time, has it gone through one or the other. And there's a way of organising this such that at t equals 0, 0 coincidence time between these two, you should detect no photons, and when you have delays between these measurements, you should detect several photons. Okay, so there's some data that was collected just today downstairs, and this takes a little while to fire up. But basically, you see that at time t equals 0 here, where there shouldn't be any photons, you actually see a dip in the coincidence rate, and this is characteristic of a single photon source. And in fact, how much that dip goes down to 0 as you collect the data is indicative of the quality of your single photon source. And we now, I believe, hold the record for how far that goes down towards 0 by several orders of magnitude. So the guys down in the lab have done an amazing job in setting up this equipment so that there's very little background and dark counts and all the rest of it, and have a very good quality single photon source. Okay, so that's one part of the technological tree that I want to go through. Quantum computing, finally quantum computing. Okay, we'll see how we can do this in time. Okay, so I did have a few slides on the way we try to understand the world is often connected to how complex a calculation we can do. So one example is we know the theory of protons and neutrons, making up the nucleus of an atom. Okay. We even know the theory of quarks and gluons, which make up a proton, and that's the more fundamental theory. Okay, so we can write down that theory of quantum chromodynamics, which describes quarks and gluons, and it's basically just a very short line of mathematics. That's the theory. Okay, but and that was written down in the 70s, but nobody has really solved that and proved that the proton mass is what it is based on that theory, because it's just mathematically so hard to use, and so we put it on a computer. And indeed, that is one of the problems that's driven computer research for many decades, to be able to do such a problem. And so what's the result after, 3 decades of trying to solve quantum chromodynamics? We know that we can calculate the proton mass to about 10%. Okay, so a lot of effort goes into trying to verify, is that our true understanding of that particular corner of the universe? And it's all based around on how much we can actually compute. Another example is, say we want to understand protein structure, how a protein actually folds. Well, if you made a petaflop machine, and this blue gene machine is touted as such a classical computer, that means that it can perform 10 to the 15 multiplications of a very long number by a very long number per second. So 10 to the 15 very large multiplications per second, which is an amazing amount of computational power. And then you ask, okay, if you set up a protein folding problem on such a computer and you just let it run, and it's basically just doing an electrostatic problem, right? It's got many thousands of atoms, but it's still electrostatics. It would take it well over a year, I believe, to actually solve that problem with that amount of computing power. So there are lots of problems around us in nature that we need to solve on computers, and the solution represents in some way our understanding of that particular system. And so a very good question is, well, how fast can computers get, and what is the limit? Because we are heading towards a limit. We're very comfortable with the fact that our PCs and laptops are getting smaller and faster, but you also notice they're getting hotter every time we get a new one, right? So there's this thing called Moore's Law, where the speed of a processor, an Intel chip, will double every 18 months. And that's basically because they can get more transistors down on a given area of the chip. They're making the transistors smaller and smaller and smaller until the junctions of a transistor now are at the level of 20 or 30 nanometers in size. And so we can see the number of transistors on a chip as a function of year, and we can see this steady rise as we march along. But pretty soon, they're going to get so small that the transistors themselves will be essentially the size of an atom. And I've been collaborating with some people in Holland, a place called Delft, where they've actually made a transistor out of a single atom, where electrons or current will actually go through the energy levels of a single atom in silicon. And the thing is that doesn't behave like a normal transistor, and you need quantum mechanics to actually describe that, and that's the trouble. To make these small elements behave deterministically, classically, like you would like them to, you have to put lots of voltage on. And that's why these things are getting hotter and hotter and hotter. The power densities are getting quite large. And so people are thinking that pretty soon, by maybe 2020, we'll be basically at the limit of how many transistors we can pack into a given area. And so people think, oh, it's just the end of the road, and people are getting very nervous because that's not very far away from a company like Intel. And we would say, no, that's not the end of the road for computing, because if you just embrace the quantum and make a quantum computer, then all of a sudden your computation power will increase quite dramatically. Okay, so we now know that quantum mechanics allows for a great deal of processing power, and we can start to talk about this object, the quantum computer. How do we know that? Well, let me just explain. Now that we know something about superposition and everything like that, I can do this a little bit more quickly. So let's imagine we have an atom. So here's the, it's not to scale obviously, the nucleus and an electron. If it was to scale, no, never mind. Let's just say that that's our cartoon of an atom, and we hit it with a particular laser. Well, we can actually arrange the laser such that the atom is now in one of these indeterminate states, a superposition of the atom being in its ground state and in an excited state. It can be in both possibilities at the same time. Okay, I've gone through a great deal of trouble to explain why that's so, or perhaps not why that's so, but that it is so. And if we label the ground state as a 0, and we label this excited state as a 1 to connect us to binary numbers, we can write this whole combination as the 0 possibility and the 1 possibility at the same time. Okay, this is superposition. And so, well, if it was a classical bit of information, it would be 0 or 1 only, and this would just be the voltage 0 or 10 volts or whatever. But it's a quantum bit of information. It's an atom which can exist in two states at the same time. It exists in the 0 state and the 1 state at the same time. And so we call these qubits quantum bits. Okay, now imagine we have 3. And this is where we start getting into the inherent power, processing power in quantum mechanics. We have 3 atoms. And we hit them with a laser pulse, the same laser pulse. Each one of them goes into this superposition of 2 realities. But it's actually more than that. If we consider the whole thing as a quantum state, then we describe that as, well, part of it is this atom here and its superposition. We multiply that by this superposition and that one, and it's actually in 8 possible realities at the same time. And you notice the way that I've written it is that the realities are just labelled by binary numbers. Binary numbers 0 up to 7. Okay, so we start to connect with information and binary numbers. So 8 possibilities can exist at once. And so you have the possibility of a quantum register where you have all of the integers representable by 3 qubits existing at the same time. Okay, so we think of binary numbers in this way, and that allows us to put up that joke, right? That, you know, if you don't know about binary numbers, you think there are 10 types of people. Well, what are the other 8 that know this is binary for 2? Okay, so now you know that. Okay, so somehow the quantum state of 3 atoms can store 8 binary numbers. Okay, so let's take that to an extreme, well, more extreme case. So for 3 atoms, we had essentially 3 times 8, 24 bits, 3 bytes of quantum information. Now let's just take a modest example, 64 atoms, and do the same sort of calculation. It's got this many numbers stored simultaneously in the superposition. And, well, if you were to translate that to hard drives, it's like 1.37 billion hard drives of information. But it's quantum virtual information, all right? As soon as we try to look at this wave function, it'll collapse into one of the 8 possibilities. So the trick is to do something with that information before we look at it. And that's what a quantum computer has to do. A quantum computer would have to prepare such a state, and then we would have to manipulate every single atom that stores information such that we do a calculation on these binary numbers. And then, and only then, do we do a measurement and have a look at the system and hope that the measurement outcome is related to the answer of the problem that we are trying to do in the first place. Okay, so there's a problem though. So all that sounds okay, but there's a problem because whenever we have a superposition like this, in nature, nature doesn't like this because you can't isolate anything like that perfectly from the rest of the universe. The rest of the universe unavoidably interacts with these 3 atoms. You can try to minimize that interaction, but the interaction is there. It's always there. And when that interaction is there, the rest of the universe acts like it's doing a measurement, acts like it's doing an observation. And this is a process called decoherence. This is called a coherent state because there are these well-defined coherences between all possibilities. The environment wants to decohere that state and to force it into one of the 8 possibilities. Okay, so if we want to make a quantum computer that has these coherences, these very large superpositions of possibilities, or if you like, is navigating through the multiverse of different universes, then we have to guard it against the environment as much as possible. But even then, that's not enough. But what you can do is you can redundantly encode your information in many qubits. You can have, instead of a single 0 being in a single atom, you can have a 0 being encoded in 10 atoms or more atoms. And you can allow certain parts of that combination to interact with the environment. You can look, you can measure other parts of that and deduce what error happened across that whole larger qubit. And that's called quantum error correction. And it's only with quantum error correction that quantum computers are actually feasible. And that's why it's very important to know and understand that. But for us, it just means that there's a way of protecting against the environment. So the quantum computing timeline, just the early milestones, I guess. Well, first of all, it was sort of started off in the early 80s with Feynman and Benioff from information theory. And then David Deutsch came up with a quantum algorithm that was very simple. And it was basically just a simple binary yes or no type problem, which he could prove that a quantum computer could do in 1 step that a classical computer would take 2 steps. Okay, so it was a little bit faster than a classical computer. And that was in 1985, and then in 1984, Peter Shaw came up with an algorithm that was just amazing because compared to this yes or no, but still very important algorithm, he was able to show that a quantum computer could factor very large numbers into their prime factors. And that's a very important problem because that's precisely how all of your bank details are protected on the internet through what's called RSA encryption. And RSA encryption relies on the fact that if you have a very large number of several hundred digits, it's very difficult to find 2 factors that when multiplied together give that number. But it's extremely easy to take those 2 factors and multiply them together and verify that you get that large number. There's sort of this easy direction and hard direction. And so that's the way everything is encoded. And so all of a sudden, we've got an algorithm which is exponentially faster on a quantum computer than on a classical computer. And ever since then, there's been very rapid progress. Okay, so what could it do? Well, I've just said one thing it could do. Grover came up with an algorithm to sort through a list of objects. N objects would take you N on 2 lookups. It's like looking through a phone book that's not in alphabetical order for somebody's phone number. Okay, not easy to do. But on a quantum computer, you only take the square root of N to do that. So that's a bit of a head scratcher, how that works. But Shor's algorithm is the following. So we have two numbers which, when we multiply them together, gives us this large number. That's very easy to do. But to go from the large number and find those two factors is very difficult. And the larger you make this number, it becomes exponentially more difficult to do that. But on a quantum computer, it doesn't become exponentially more difficult. And that's one of the great things. Simulation of quantum systems is not surprising. If you make a quantum computer, one of the things it can do is simulate a quantum system. And that could be very useful for quantum chemistry. And even though there aren't many algorithms yet that a quantum computer can do exponentially faster than a classical one, there is just so much interest in this area that there are lots of people looking for these. Okay, how do we make a quantum computer? Well, there's lots of technologies out there that people are trying to implement qubits upon, but there are many conditions that you have to satisfy. So that to my mind, there aren't many really feasible proposals out there. There are things like you can trap ions and allow them to move about and basically interact with one another, representing the qubits. You can even make superconducting circuits act like qubits. Photons can act like qubits. And one that we're trying to make is based around electrons and solids. And so this is an idea that's based around Bruce Kane's proposal in 1998, which is to place individual phosphorus atoms at particular places within a silicon substrate. And silicon is crucial here because one thing we do know about the computer industry at the moment is that everything's made in silicon. And they know how to pack a lot of transistors and electrical gates onto silicon wafers. Okay, so this is a very important proposal because it links directly to very large-scale CMOS technology that's available at the moment. I estimate to do a very large factoring problem on a quantum computer, you would need hundreds of millions of qubits because of the redundancies you require for quantum error correction. And so that means that your proposal has to be able to deal with such numbers of qubits and controlling these. And in my opinion, one of the only ways you can do that is to link up with current CMOS technology. If nothing else, try to calculate the size of such a machine if it was based on superconducting qubits where each qubit is maybe a millimetre by a millimetre. It starts getting very large and then you've got all the control. So in my opinion, one of the more feasible ways to go ahead is to do it in silicon and link in with CMOS technology. And that's one of the big arguments that we use to drive our research forward. So here at Melbourne University, David Jamison's group is looking at building such a device by firing in phosphorus atoms into silicon, and they fly through the lattice and they stop eventually. We put gates on top of those, and by manipulating the gates we can manipulate electrons to go between those two atoms, and we're trying to march towards making those devices into qubits. Another way to do it is based around Michelle Simmons' group up at the University of New South Wales, and there you take a surface of silicon, you cover it with hydrogen, you can come along with a scanning tunnelling tip and pull off hydrogen atoms at particular locations, virtually drop in your phosphorus atoms, which will then go into those holes that you've made, get rid of the hydrogen and grow over with silicon. And so you place these phosphorus atoms where you want them. And it's interesting to have a look at the sort of scales that's involved here. Here's a typical chip that we can see, and what we're doing is operating at this sort of small area here, it gets smaller, microns, but we're actually talking about the nanometer scale. These are pictures of the individual phosphorus atoms lying on the surface. And we want these to be typically 10 nanometers, 20 nanometers apart, and we put gates on top of those, and we want to control these in all the ways that are required to do quantum computation between them. Okay, so I'm going to show you a little movie to finish, and this movie is based on those current ideas, those original ideas that came in 1998, which started our Centre for Quantum Computer Technology in Australia. The Australian government has put a lot of money towards building a quantum computer in that paradigm. That proposal was very important, but as we learned more and more about quantum computation and how complex it is, it soon became apparent that that would never work. And we had to do a lot of things to modify that, and we finally converged, and most of these ideas came out of our group here, the theory group, in quantum computation here at Melbourne. And we've written several papers, and this has come to the notice of the US government, where we do get some of our funding, and they commissioned an animation, and this is the first pass go at the animation of what the quantum computer would look like, because it's very important to start to try to visualise what this machine would be in order to try to get more funding to actually try to build this. So we're going to see several things as we go through the movie. The first one is a representation of the Silicon Lattice itself with individual atoms. And here we have one silicon atom that's been replaced by a phosphorus atom, which has 5 valence electrons, 4 of which bond with the rest of the lattice. And what we see is the probability cloud of the remaining electron. That's not to say that it exists as a cloud, that's its cloud of probability. I didn't have time to go through atomic clouds and everything like that. That's a representation of where that electron might be in space. Our qubit is going to be the spin of that electron. In other words, how that electron can respond to a magnetic field in 2 ways, either in a spin-up state or a spin-down state. One we call 0, the other one we call 1. So that's how we encode our information. So all the rest we don't need to know for the moment. So this is now looking from the electron cloud up to the surface of the silicon. And on the surface of the silicon we have a gate, an electrical gate which is about 10 nanometers wide. And these lines represent putting a voltage on that gate. And what does the voltage do? It sees an electric charge and it deforms that charge. It deforms the way that the cloud of probability of the electron actually exists in space, and you can actually pull it into different shapes. And as we do that, we change that 0 to a 1 or to a different combination of 0 and 1. Okay, we're affecting the spin of the electron. These spheres here represent the quantum state. It's called a block sphere representation. It's way too technical for this visualization, but we couldn't resist putting it in there. Basically, up the North Pole is a 1 state, is a perfect 1 state. At the South Pole, it's in a perfect 0 state. And anywhere else on the surface, it's in a combination of 0 and 1 at the same time, but a particular combination. And this little one, don't worry about it, it's all the other electrons that we're not concerned about. Then we'll see there'll be, okay, we've got this gate here controlling that cloud, this gate here controlling that electron cloud, and this one in the middle allows the clouds to know about each other, draws them closer together, these electron clouds, and allows them to interact. And it's this interaction which is at the heart of generating processing, that you start to change zeros to 1, conditional on one or the other. You have elementary quantum logic gates, and it's this interaction which does that. And then we have to move the electrons around. This is highly non-trivial to do, but we found ways theoretically to do this. This is a procedure called CTAP that was invented by one of my postdocs, Andy Greentree, coherent transport by adiabatic passage, but that doesn't matter. What it does is teleportation. It will take an electron cloud from here, zoom it through intervening space without occupying it, and allow it to reappear here. And these gates above on the surface are the ones that enact that. Okay, we'll see that. And then finally, there's a readout process where an electron over here will selectively tunnel depending on whether it's a 1 or a 0. It's basically being observed, and it goes into this big chunk of metal called a nano Schottky reservoir. And when it's in the metal, its wave function disperses all the way around in the metal, and that's why it looks like this sort of cloudy thing inside there. Okay, finally then we'll see what the computer would actually look like when we look above. All the blue dots are those electron clouds, and they've been moved around all the time. They come into regions here where they interact, and then they move around, and they might go and interact with something over there, depending on how this whole thing is being controlled. The movements that you actually see are the exact movements that you require to do all the quantum error correction on these qubits. Okay, so I've probably said enough.
Let's take the lights down.
Yep, I'll do that. I've just got to navigate my way back. Find my cursor. Okay, I'm not going to find that way. Oops. I think I have to run it this way. The way the screen is going. I want to run it full. Well, maybe if I do the screen here. No. Yeah, there is a soundtrack. But I've got the plug-in. So we're applying a magnetic field, and that causes that electron state to start going around the Bloch sphere. But that's a very complicated quantum motion, so we mathematically transform to a rotating frame. So we're not rotating the computer, we're rotating us. And then the evolution becomes very simple, just around a great sphere, a great circle of the sphere. So it's going from 0 up there, or 1 up there down to 0, and a very simple path. Okay, that's just a mathematical way that we use to view the state. Now we start to apply an electric field, and that distorts the electron probability cloud, and that changes the path of the quantum motion. So it's now going to a particular superposition of 0 and 1, and it's actually the exact superposition of 0 and 1. And looking from below, this is affected by the gate, and the gate is 10 nanometers wide. Now we have what's called a C-NOT gate, a control NOT gate between these two electrons. And that's a particular sequence of single qubit gates. This 2-qubit gate, when we turn that one on, it draws the electron clouds together. And there'll be another one over there soon as well. There should be. So this is a complicated series of operations, but it does what we want, a C-NOT gate. Now we want to transport it from that location back there, and you see just faintly these atoms in between that define a pathway that goes from here to there without actually seeing any of that pathway. And now we want to observe it, and so we do this tunneling to the nanoshocky reservoir, and that'll tell us whether we're actually predominantly in a 0 or a 1 state. And with the groovy music swells, and we start to see the actual operation of the computer. We see these electrons whizzing about, they're interacting, and this is actually a schedule for doing quantum error correction, that each bit of information is actually encoded in 7 of these, and that's why you see groups of 7 moving, interacting, and moving away. A lot of that was worked out by one of my PhD students, actually Stevens. And then we pull back even further and you see that we have very long lines of these qubits interacting as we need to actually do something as complicated as Shor's factoring algorithm. And this is representing Shor's algorithm here, and we have possibilities of the whole computer, which if we choose one, can take an encrypted piece of information like this and crack it. So, it doesn't always get the right answer, that's the thing. Okay, so I hope that's shown you a little bit about what a computer could look like. And okay, so I just want to finish with some quotes. I realise I've gone over time a little bit and I apologise for that. But of course, Einstein really didn't like quantum mechanics. And so, but then Niels Bohr, I think, got tired with Einstein using the word God. So let me finish there. Thank you very much, everyone.
Tonight we've seen the equivalent of being back in 1947 when the first transistor was unveiled, and you can imagine that in 1947 they did not know where that was going to go, but tonight we've seen the first quantum transistor unveiled, and with the full blueprints for the $2 million fabrication facility to turn that into a Pentium chip in one go. That's an amazing scope to go from the fundamentals all the way to a fully fledged blueprint for a large-scale quantum computer worked out in tremendous detail. So I'm sure, Lloyd, yes, that's the first time those blueprints have been shown anywhere in the world, and I think soon widely across the US to various Congress representatives and chief scientists. This movie will also be shown in the near future. So I'm sure Lloyd will be happy to answer a couple of quick questions. If anyone's got a burning question, yes, gentlemen at the back.
Last time we visited this area in the July lecture, there was some sort of competition, I think, to get quantum computers to factor number 15. And there was even, I think, maybe a prize associated with that. I'm wondering if there's any move that's been made forward on that.
That was done using NMR, quantum computation, which is basically a glass full of liquid of particular molecules. So there's essentially 10 to the 23 individual quantum computers. And it was using molecules of a particular length with a certain number of atoms in there, and the nuclei themselves had magnetic spins, and they were the qubits. So it was first done, I believe, using liquid NMR.
And how long? Some time ago?
4 or 5 years ago. Yeah, it was a while ago now. There's been a lot of progress since. Doing things like that are very important. I think people have factored 15 in various different ways. But the really important things are to try to understand things like if you get a certain number of ions in an ion trap, are they actually entangled? And so one of the big things, to my mind, that happened in recent years was the entanglement of 8 ions in an ion trap, and to actually prove that they were actually entangled. So they had to do a certain number of measurements on those ions, and then they used all the computing facilities of Vienna for several weeks to actually then prove that that data represents that those atoms are actually entangled. So there are quite important sort of lead-up steps to the technology, but these things like actually running algorithms are very important just to show the proof of principle.
Take a second question from the gentleman right at the back.
What sets the speed limit of the computer?
The speed limit of the computer, that's a very good question. Those gate operations are basically the speed limit. So, of course, we've slowed it right down, but those operations, and I should have said this, are occurring at the nanosecond level. And those transportations are also at the nanosecond level. And that means that we have to be able to control things over nanoseconds as well. Now, you can slow it down so that you can get better control, but the more qubits you have and the more layers of error correction, this is a thing I didn't mention, but we redundantly encode our physical qubits into groups of logical qubits, and then we do another layer of that, and then another layer of that. So in the end, one qubit might be made up of thousands and thousands of electrons. All of a sudden, the effective time scale at that upper level is very slow. It might be microseconds or even milliseconds. Okay, so your final timescale of your quantum gates might be slow, but the thing is that you have exponential speed up over the classical counterpart. So the very opening scenes of the movie took us a long time to work out that ratio, that comparison, that if you wanted to factor that number using a classical computer with current technology and capabilities, it would take 1 million years. And then we had to say, okay, well now imagine a quantum computer with a certain gate speed of the order of nanoseconds, 100 million qubits or whatever it took, that many layers of error correction, how long then would it take it to factor that number? And that's where the number of minutes came from. So that was all included.
Well, ladies and gentlemen, I'd like to bring the proceedings to a close tonight. But I'm sure if you've got a pressing question, Lloyd would be happy to stay for a little longer to answer it. If you'd like to keep in touch with the School of Physics and like to be added to our mailing list, there's a sheet out at the front door where you can enter your email address, and we're very happy to notify you of future events. I'd like you to invite you back next week and the following week for the 2 further lectures in our 2007 series. I'd like to thank Steve and Nick for setting up the audio-visual for tonight. And finally, I'd like to thank you all for coming and look forward to seeing you again next week. Thank you very much.